But right, okay. So good evening, guys. Today we are going to be doing like elementary number theory. Like this is an intro class, so it would be quite basic on the like prerequisites. In fact, there's no prerequisites. Like please talk. Like that's important. Like if you talk, then you'll be able to learn more. Since I will be able to speak more, and hence like it will be better for the both of us. Right? You would want to learn the most of out of your like 1.5 hours of slot. Okay. All right then. How do you screen share? Uh, Screen. Start broadcast. All right. Oof, cut off. Okay, now. So today we are just gonna touch over like basic number theory. First of all, like there are what differentiates number theory from like algebra and combinatorics. Like it's basically the study of numbers, no? So what like there are many ways to look at numbers in some sense. Okay, 1 second. Numbers. Like so you know about primes, no? They have like multiplicative structure, and you can also add numbers. Which is like and switching between them is like basically the key to like solving more problems, which is called basically shifting perspective. Because like why multiplicative? Because you have primes, right? And then in fact, like you can every number is built up of primes. So primes are actually a very like interesting object to study. We have like gotten lots of stuff about primes, but we do not yet know like the pattern of primes and stuff in that sort. In that sense, like suppose take any number 15. Instead of looking at 15, you can individually look at 3 into 5. So yeah, that's one thing. But then there's also the additive structure. This is mostly like the algebraic part. For example, you can just have say 7 plus 49. Does like can anyone speak up about like what like, I know this is a pretty niche application, but what could we expect after the addition of this? Suppose we had something like yeah, like is there something nice about the addition? 7 plus 49. Anyone? Like
You can get a multiple of 7.
exactly, yep. See, this is what you did right now is just basically jump from the additive like algebraic like thing to like the number theoretic aspect. Indeed, like you can write it as a block of some numbers, and in fact, we have some nice idea about those numbers. And in like someone said in chat that B7 of 7 plus 49 is equal to 7. What? No, it's equal to 1. But like yeah, sure. Uh, which like when we'll be doing VP, like either me or some other guy, like this intuition is gonna be like very helpful in the long run. Anyways, like that's enough about me yapping out numbers. Now, how many ways are there to solve a number theory problem? Anyone? Like the question is, how many ways are there to solve a number theory problem? Infinite. That's correct. Like to some extent, yeah. But like that's not the point. Obviously, there are gonna be like infinite ways to solve the problem. Like okay, there are epsilon underscore one m. Point is that every number theoretic, almost every number theory problem is composed up of these aspects. At least the ones you see in like uh, olympiad level. Say there's the obviously the number theoretic aspect. There's the algebraic aspect, and there's also the combinatorial aspect. And then like once you get very grown up, there's gonna be stuff like analysis and whatnot, like calculus, everything involved. It is like a part of the analytical number theoretic branch. Like it's very fun to study these things. Like I implore you, you should study these things. Like one day, imagine you become like an analytical number theorist, and then you can say this class was the reason you started, or something. I don't know. Anyways, yeah. So usually juggle between these aspects. Obviously, since this is a number theory problem, you should use the number theory aspect, and then there's the algebraic aspect. Some like there's a common saying, like me and a few other people say, like all good number theory problems are actually combinatorial problems, which is like basically just saying that combinatorial aspects, like combinatorial aspects are like very nice. Like they basically like the good problems you see today are mostly like combinatorial in nature. Like there's this one 2002 and 4 or something. Like that's a very good problem. And yeah, like I mean, yeah, that's kind of false to some extent. But like combinatorial aspects like add some sort of like flavor to some like number theory problems. Anyways, like moving on. But in this lecture, we'll mostly cover these two, and we'll show that basically the leverage you'll obtain by solving these problems, like while solving these problems, is when you shift from the algebraic perspective to the number theory perspective. This is like double counting in combinatorics, if you have heard of it. Like ignore that, like that's some random thing. That's not really random, but like that's a very important thing. So yeah, the switching of these aspects is basically what gains you the leverage. Otherwise, you'll just be stuck in a line trying to do stuff. Okay, like I will not be able to explain this very, very properly. So let's just try to deal with this in a problem. Like we'll cover some theory like after this, but this is like minimal theory. So yeah, wait. Okay. So like I will not give you time to try this, but like yeah, I'll give you time to try this. Like try it for 1 or 2 minutes. So yeah. Basically the point is you are given a very niche condition. A square minus BC is a square, and then you have to prove this random looking number to be composite. Like how could you motivate this? How could some number of that form pull up? Like some hint for you all. Like it's very minor hint. But like see, this is a quadratic term, no? Like if I were you, like I would like there's some nice way you can jump down degrees. Like when you get more like experience with number theory, you'll want to jump down degrees very like a lot, or sometimes lift up degrees. This can be seen in like VP stuff, like LTA and stuff. But like one of the ways you can do this is by factorization. Like there's also another like proof to this, but like we'll be discussing the factorization proof. So yeah. Anyways, yeah. So try to factor this polynomial in some sense. Obviously, like since you want to exhaust the conditions, if you can exhaust every condition in a number theory problem, you can be almost certain that you're gonna solve the problem. Okay, not okay. No, that's misleading. But like you have to at least exhaust almost all the conditions. By exhausting, I mean like you should use up all the conditions, unless it's a troll problem, obviously. And then like at least you have to do that before solving the entire problem. So yeah. So one of the ways you can do this here is like pretty simple. You just write it as like a square minus bc is equal to k square. for some integer k.
Can you use
Now,
parity?
what?
Can you use parity or like kind of factorize a square minus a square?
What? Can you?
Can you use parity? Parity.
Parity.
Maybe.
That's, yep,
Well,
that's a thing, right? Oh, wait, right. That's like, that would give us some stuff. So yeah, like I, I think the fact you motivated this like stems up from the fact that he, if that's even, then that's like obviously composite, right?
yeah.
Yeah, that's a great idea. In fact, like this is one of the natural things you start at the first. You start your doing the problem at the start. Yeah. Oh, yeah. Anyways, so this is even. Now we just require both of these to be even or both of these to be odd. Okay. Is this clear from here? Can but like do we have some case where B can be even and C can be odd? I think we do, right? Even, odd. Like this is divisible by four. This is divisible by four. So yeah, not much leverage, but like eventually, like I think in fact 2A plus B plus C will prove to be even or something. Okay, not probably even, but I'm not too sure. Like we'll just walk through this. Anyways, 2A plus B plus C from this thing. We want to get 2A plus B plus C in terms of these things via factorization. Like, okay, so the first thing I want you to notice is the fact that A is independent of stuff, and like A is turning to A. Like, what like give me any ideas how you would like try to convert A into 2A? And, even in fact, any ideas like dumb ideas are like also appreciated because they usually like in the end lead up to a solution. A plus one whole square. Yep, that's an idea. Like, in fact, think simpler. Like, you would want to a whole square to come up, right? So how do you do that?
Multiply by 50.
Yep, exactly. Great. Like that's the part. So after multiplying by 4, you would have that 4a square minus 4bc is equal to 4k square. Now you have the 2a square term minus 4bc is equal to 4k square. Uh, yep. Now what? Like now you want the b plus c term, which is independent of a, obviously. And now, but you have the 4bc term, which is like, yep, that's something to say the least. Uh, Nice. Like I see this like comment in the chat by like once 4bc is equal to b plus c whole square minus b minus c whole square. Yep, that's exactly what I was looking for. Like 2bc seems like very recognizable, no? And hence you motivate that. So in that sense, you would have b plus c whole square minus b plus c whole square uh, plus b minus c whole square is equal to 2k whole square. Okay. And yeah, now we have the b plus c. And now we have this thing. So like let me swap pages. Like I'll do the like hard work for you. Like not really hard work, but work for you. 2a plus b plus c is equal to 2k minus b plus c. All right. So I think at this point, like we have come up to a point where we are ready to directly attack the entire condition we are given the problem. Okay, so if this is a prime, what does that imply? Anyone? Uh, like anyone in the chat? Very well. Here's something. Okay, so right. Is that the LS? Oh no. Yeah. So since this is a prime and all numbers are made up of primes, and primes are the fundamental building blocks of everything, we okay, I'm yapping, but like the main point is 2a plus b plus c. Yep, exactly. P divides AB implies P divides A or P divides B. Yep. So we would have that without loss of generality. Can we assume that it divides 2k minus b plus c? We could, right? Because B, it's the entire thing is symmetric in B and C, right? So let's assume it divides 2k plus b minus c. Okay, interesting. Wait, but like, don't you think this is like too good to be true in some sense? Okay, I'll just. This is a relatively easy part to understand. Like you would have that 2a plus b plus c divides 2k plus b minus c plus. Actually, no, I should like explain this part properly, even though this is a fairly trivial part. Okay, so 2k plus b minus c by 2a plus b plus c is an integer, right? Add 1, it should still be an integer, though. Wait one sec. Like, yep, nice. So we would have that 2k plus 2a plus b is divisible by 2a plus b plus c. See, like we can do this because like the entire thing is symmetric in B and C, no? Like, okay, assume that 2k plus b minus c is actually not divisible by like 2a plus b plus c. What we do then is like ignore the mathematical part. We just invent a new alphabet where B stands for C and C stands for B. All right. Then like 2k minus b plus c stands for 2k plus b minus c in a new alphabetic system. So yeah, because okay, so the point is this thing and this thing are symmetric in like B and C, like this entire expression. So it's fine if we like assume any of the factors to be divisible by that. Right. Okay, nice. So it was 2b here, and now is the crucial part where we use like the like initial observation pointed out by like Aditya. Okay, if 2a plus b plus c was even, okay. If 2a plus b plus c was not even, then like we would not be done. However, like this factor would not be required, no? Oh wait, what? Why did I stop screen share? Bhai? Only the host can share this meeting, and the online math club is the host. Wow, absolute cinema. Oh, hang on, just give me a second. There was some issue with the meet. Ah, okay. Yeah.
Yeah, I think you should be able to share now.
Okay, right. Thank you. What happened like to the class? I think everything was pretty fine now.
I think some students were not able to join for a while, so I think there was some issue with
Oh,
that.
I see. Oof. Oh, right. Like you have to check on stuff, right? True. My bad. So, okay. Now, initially pointed out by like Aditya, what if what if 2a plus b plus c was even? Then this factor would matter. But then this problem wouldn't matter because like 2a plus b plus c is even. So it's like, and it's obviously greater than equal to 4 since a, b, and c are natural. So this entire thing, 2a plus b plus c, would be divisible by 2 and hence composite, hence also greater than equal to 4. You have to like write up these details whenever you like write up on paper because that's important. Like usually those lead to docs in like stupid contests like RMO and stuff. So yeah, like keep that in mind. So otherwise, if 2a plus b plus c is odd, then what do we have? This entire factor of 2 does not matter because like it is coprime with 2a plus b plus c. And since it's coprime with 2a plus b plus c, no factor, no prime from here could possibly like this is basically an extra term in some sense. So we would now have that 2a plus b plus c divides a plus b plus k. However, uh, like this seems to be false, no? Like k is some number, 2a plus b plus c is some number, a plus b plus k is some number. But this seems to be very smaller than k, no? Like it's off by a factor of a, like an entire factor of a. Indeed, like once you notice that uh, after simplifying out the parts and stuff, a plus c is greater than k. Now, why is this inequality true? Anyone? In fact, like I'll make it simpler. A is greater than k. Why is this true? Where was the initial equation? Like you only need this part. So why is k greater than k? Yep, exactly. So a square is equal to k square plus bc, which is like obviously greater than k square since this thing is positive. Therefore, like implies a is greater than k since both are like positive. Yep, exactly. K square minus a square. Yep, exactly. K square is half. True. Yeah. But we have a plus c is greater than k. So intuitively, this thing can't happen, right? Since you would have something like the numerator is like 100, but then the denominator is like some random number. I think that's easy to understand enough. But like if any doubts, actually no. One second. Yeah, this can't happen. Why this can't happen? Because like the numerator is smaller than the denominator. And here the numerator is smaller than the denominator. And the numerator is not zero. So yeah, we are done with this problem. So like I would like quickly like to take a pause. So any doubts? Like anyone, like anything, like any part that was unmotivated to any part that was like, yeah, okay, Sanskar has it out. Right, can you speak up?
I think, yeah. So my question was like, why wasn't it like obvious that B and C both are order, like both are equal? Wouldn't like this
What?
have finished directly?
What?
Like, can't we like say like A square minus B C equal to K square? Then like from what for we get B and C both are even or B and C both are odd? Like
No,
what was
right?
fault over here?
Right. Like, see, point is a square minus bc is equal to k square. What you mod 4 will give us that suppose everything is like congruent to 0 mod 4, right? You will like work in mod 4. Take this as 16, take this as take this as like 4, take this as 20 200 or something. I don't know. Like, this is obviously false, but yeah. And take C as like, some odd number, 7. Mod 4, everything is being satisfied, no? Because everything is congruent to 0. This is congruent to 0. This is congruent to 0. But in this case,
Yes.
we can conjure up something that is B is even while C is odd. So
Oh,
yeah,
nice.
like
Okay.
there's this case. Right. Mod
Yes.
4 is in fact one of the more natural ways to attack this problem at the start, which is why like we can motivate that 2a plus b plus c can't be even, and hence b and c can't have the same parity and stuff. But then we'll run into a problem. We are not able to solve the problem using this. So yeah, we would try to look for alternate approaches. We'll try to fix our approach. We'll try to take a step back, go in and suppose this is a part to a problem. If this does not work, we take a step back. We go to another path. Well, that's just yeah for now. Okay. So now, like the question of the day, the star question. Like I want you to pay attention to this part. This is like important. Like if you are lying on a bed, don't lie on a bed right now. Like you can lie on like later on. But number theoretic aspect and algebraic aspect. Where did you switch? How was the entire discussion from before used here? I'll give you some time. So when did this problem stop being a number theory, stop being an algebra problem, and start being a number theoretic problem?
When
And
we
after
use the
factorization,
divisibility.
What like uh, both people can speak like once at a time. Like
after factorization, like then we must check whether uh 2a plus b divides 2k plus bc. That's when it becomes number theory.
exactly, yep. Like any other answers? Uh, like Sanskar, you were saying something.
Yeah, so when we are after the part that like 2k plus, when we argue that prime divides one of them, the number theory part started.
Exactly, yep. So see the if the problem we wanted to prove the problem, we never got anything. Like we are not able to make any progress until like the key part of the problem came after we did after we dealt with the initial stuff, and then we would have the 2a plus b plus c term. We'd want to utilize the condition in the problem to prove that this is a contradiction. How can this be a contradiction? Like unless it's a so if it is a prime, it must lead to a contradiction, which is why we are so confident with this method of approach, right? Because like yeah, it would at least give us something.
I just
Anyways,
have,
yeah, there's that. Yeah,
can we like use a different method like a squared minus
right.
bc k squared, and
A square
then
minus
yeah, you transfer that k squared to the left hand side and bc to the right hand side,
a square
and
minus k
then
squared is equal to
you factorize the left hand side to get a minus k into a plus k equal to bc, and then
yep.
you take casework like whether a plus k is b or a plus k is c, and then you write a b
A plus
c in like yeah.
a
So
plus a
assume that a
yeah
plus k is b and a minus k is c,
yeah
and then you write a. You substitute a in that 2a plus b plus c. So a becomes b minus k, 2b minus k plus b, and yeah, you can also write c. Wait, um,
yeah. I mean both are basically the same, no?
you can also write c in terms of b, I guess, because you
See in
can
terms of
a's c is a minus k, and you substitute a in here in this equation. C is equal to a minus k. A is B minus K, so C must be B minus 2K, right?
C is equal to B minus 2K. Right.
Yeah, and then you substitute C in this 2A plus B, and now you
Yeah.
just add up the like terms, you're gonna get 4. Yeah, this already proves that this is gonna be impossible.
Yeah. Like the entire part, before assuming that B and C are the things, like the factors, after that it's like easy to deal with. But why would this hold to be true, right? Like,
It can also be C and B. You're going to get the same.
yeah, I know it can be C and B, but like suppose uh B was some product of like any number of numbers, like B is of the form PQRS and C is
Okay.
of the form like LMNOP. Now A plus K can be like some random niche thing, PLMN, and A minus K could be like QRSOP,
Okay.
right? So
Yeah.
like
Okay.
it is yeah, but that's
Yeah.
a nice approach. It would have worked out if like B and C were like primes and stuff. You would have to
Yeah.
deal
If
with it
there are
easy.
primes, I
Yeah,
think this must have worked out. Yeah. Okay.
yeah,
Got
exactly. That's a nice setup. I like support that.
primes.
Anyways, uh, is there anyone like I want to check? I have to check like occasionally to see if there are any people that are waiting in the meeting. So yeah, nice. Okay. None. Uh, what was I gonna do next? Right. Okay. Rational numbers. What do you think about them? Right. Like, suppose you see a problem. Like, suppose I'm not going to solve this problem, but like, let ABC be rational numbers, a positive rational, and prove that A to the X plus B to the Y plus C to the Z is square given some condition, blah, 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 X, Y, Z, blah, blah, blah. So, what do you think about rational numbers? Are they like, the point I'm trying to make is that in number theory, all rational numbers are they basically behave like integers, right? Almost like there are a few exceptions, but in modular arithmetic, they basically behave like integers. So rationals are basically integers in number theory. This is a very key like realization to have. Sometimes problems can give you like stuff in terms of rationals instead of integers. But like the main thing to realize is that whenever we work with the rationals, we never explicitly use the P by Q notation. Sometimes we just do stuff normally. No, like normally as in how you would have like executed the problem with integers. Like obviously this does not seem to be like so obvious at first, but like I'll try to give some points to help you like be comfortable with the idea. Okay, so have you guys like heard of inverses? Right, have you guys heard of like inverses in number theory, such that like given a number A, you can find some number, say B, such that A, yeah, X actually. Like that's the good notation. Always use good notation, guys. Like, they will help in the long run. Trust. Anyways, AX is congruent to mod 1 mod P. Given an integer A, you can find some integer X such that AX is congruent to 1 mod P. Is there any exception to this case? Like, there's a clear exception to this case. Like, yeah, uh, 6 what? But I don't understand. Like, yep, exactly. P divides A. You are right. If P divides A, then the entire thing is just zero, and hence you can't find like zero multiplied by zero times any number is just zero. So yeah, you can't like make it multiply once again. Okay. So yeah. So there's standard notation for the inverses and stuff. Like you can write the inverse of x, inverse of a as say a dash, a inverse and stuff. But the one notation I want you all to pay like careful attention to is 1 by a. Doesn't this seem to be odd? Have you seen this somewhere? A inverse is equal to 1 by a. This is very special. Like this basically answers the entire thing, at least for like to some extent. It isn't the condition for them. Yeah, exactly, Kausal. That's the point. Like A can't be congruent to like 0 mod P. So yeah, and if A shares a GCD of 1 with the prime, that basically means that P divides A, right? No, P does not divide A. Else like P divides A if the GCD is anything but 1. So yeah. Okay. Anyways, now consider any rational number. Consider any rational number, say P by Q. What is it congruent to in mod P using the discussion from before? Okay, I'll just write this down. But like P by Q, no, it actually does like necessarily mean that P divides A, no? Because like P is a prime. P by Q, I know now.
This should be
Take
0.
what?
This should be congruent to 0, isn't it?
This should be 0.
Yeah.
Oh wait, bruh. Oh, very bad note. This is what I was saying at the start, no? Like if you take a bad notation, like you should always take a good notation. Like in the end, bad notation is only gonna hurt you and the graders and literally everyone reading a proof. See? So yeah, thank you for catching that. So okay, in today's question, like what is x by y congruent to? Modulo p. So obviously x and x by y can act like any rational number. So yeah, if we can answer this question using the discussion from here, we can finally like establish the connection that rationals are basically integers in like number theory almost, at least in modular congruence and stuff. So yeah, okay, like I'll just write this down though. Like this is not that deep. This is just congruent to x times y inverse. But like y inverse is very well defined though. Like it is the number such that if like you multiply y to it, it will give you 1 mod p. So in fact, x by y times y is congruent to 1, is congruent to x, since like these y's cancel out and stuff. So yeah, that's that. In fact, when you'll be studying VP and stuff, you would often notice that uh, VP of a rational could be defined. VP of a rational A by B is just VP of A minus VP of B. So yeah, there's this. Further, what do we
What is
have? What?
what is VP?
VP is some random stuff the big number theorists have made up, like to
Uh,
confuse us folks. Actually, nah, like you'll learn it soon enough. In fact, I can get it's a very simple thing. VP of A is defined as the this is like not in the lecture, but like yeah. VP of A is defined as the highest prime power dividing a highest prime power of a prime P dividing A. So like V5 of 5 is this one. V5 of 25 is 2, since 25 is equal to 5 times 5, so 5 square, so 2.
Yeah, got it.
V5 of, yeah, okay. So what would V5 of 100 be? Like anyone in the chat except like Aditya. 2. Yep, exactly. 2. Why? Because V5 is written as 4 times 25 is equal to V5 of 4 times 5 square. So 2 from here. Right. Right. Okay, so that was a side digression. Anyways, what I want to cover now is CRT. Does anyone know what CRT is? Like I kind of forgot the statement though. So like it would be nice if anyone can like remind me by writing in chat or whatever. In fact, speak up, bhai. Like if you know the statement, speak up. Right. Chinese remainder theorem. And what was the statement like? Any part of the statement. Like there's beauty to these statements too, right? Like there's this epsilon delta definition of like limits. This is very off topic, but that's a very beautiful definition. Like that's probably my favorite definition of math. Like very carefully placed and when everything just lines up so perfectly, you know. If you have heard of it, like yeah, Chinese remainder theorem. There's also some care to definitions required here. Okay, I like give you the idea of how stuff actually works. I like I'll not spoil the definition for you. You would have to craft the definition yourself. This is a challenge I'm giving you. Not a challenge, but this is something you should do because in the end, it's gonna benefit a lot when you're writing papers, when you're writing solutions to problems. Okay, wait. Mi mj ka GCD is 1 and x is congruent to ai mod mi I in, yeah, then there exists some unique m x modulo. Exactly, yep. That's perfect. Right. This is what I was looking for, no? Like you should include every single detail. Though this was not that tough, but like there are still many details you could miss out of. There are people who have not considered the MI and MAJ part like equal to one. Like their GTD should be equal to one and have lost out on marks or have like yeah proven stupid things. So indeed, X is congruent to AI. I'll just write it for the two variable case since like the other cases are like very generalizable. Mod some number C, some number D implies CD is equal to 1. Implies that there exists X. Like we can find some X satisfying these properties for any A1, A2. This is very powerful, in fact, guys. C and D must be coprime though. Yeah. What does this mean? So let's do a quick like exercise. Like I won't take too much time. This is a trivial case though. X is congruent to 1 mod 2 and X is congruent to 2 mod 3. Try to find some X. I'll just do it for you. This is like fairly trivial. Just consider the number 4. 4 is not 4. It's 5 work. Yeah, 5. Right. 5 minus 2 divides 5 minus 1 and 3 divides 5 minus 3. But no, 3 divides 5 minus 2. So yeah, 5 works. So in fact, this is highly generalizable. This is just a very niche case. I did to like teach you. Anyways, this is the beauty of Chinese remainder theorem. I will, I think I will not be using this in our lecture today, but like, yeah, there's that. Okay. Now, like, we move on to a very good problem. Like, it is fairly nice. Like, don't be like scared of the difficulty. Like, I tend to write difficulties like in classes and like when someone is solving problems because like in the end, when they are going to be writing a contest, they are gonna know the problem sources at least, right? Like if you are going to be writing say RMO, uh, Like if you are going to be trying RMOP4 in contest, then you're gonna know it's an RMOP4, right? Obviously, like by definition. So yeah. Anyways, this is like the an IMO problem. Uh, let A1, A2 till infinity be a sequence. Not infinity. That's like terrible notation. Let A1 blah 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 be a sequence. Like I'll only deal with the important part of this problem because it teaches you a lot of soft techniques. No, like you're gonna learn that uh, how to shift between algebraic terms, how to like specifically find some numbers which make your life easy and stuff. So this kind of intuition is very important to build up. So yeah, let be a sequence. Then find all sequences A1, A2, blah blah blah. Like this part is not. Find all sequences A1, A2, blah blah blah, such that an plus n times am plus n is a perfect square. I will give you some times to. I'll give you some time to process the problem. So say about like 2 minutes, and then I'll talk a bit about the problem till like 7 6 because of like 6 7. But apart from that, yeah, like take your time and like understand the problem statement. If there's any doubt about the problem statement whatsoever, like I intentionally like left out. No, I don't think I've left out, but like if there's any doubt about the problem, just ask me. So yeah, like just feel the problem statement for now. No?
That is an AM, right? AM plus N.
Yep. Like
Okay.
this is the subscript. Yeah. Okay, it's 7 o'clock. Now the main part is like suppose I'm a beginner. I'm trying to solve the problem. An plus I just make some random substitutions. No? An plus one times a m uh no sorry a1 plus n is a perfect square. Now, is there any leverage you can see for me from the problem? Like, no, right? Like, I can't see anything personally. Like, if I had something like, uh, say, 5 cube divided this, and 5 cube, like, and okay, say 5 cube divided this, but 5 to the power 4 does not divide this. What would that mean about this? Note that the entire thing must be a perfect square. Yeah, it was m in the. Oh my God. Yeah, it was m in the second term. Is that like fine? Let me write it on chat too, like for everyone to see. A underscore n plus m. A underscore m plus n. One, two, a three, dot is a positive is a sequence. Okay. Yeah. So now the question is, like, anyone can answer by like opening their mic or like just writing on chat at this point. Like if m cube divides this and if 5 cube divides this and 5 to the power 4 does not divide this, what what must divide a1 plus n?
Wait, 5 cube divides an plus 1 into a1 plus n?
5 cube divides an plus 1.
Okay, so 5 to the power 4 does not divide
Yeah,
an.
exactly.
Okay, so it shouldn't be a multiple of 5. That's one thing. Like a1 plus n.
Exactly.
Yeah.
Exactly. That's the entire thing we are going to require in this problem. This is the key intuition which was required to solve the problem. See,
Okay.
why would we even think of this? Like, do you have any answer to that, or like should I answer? Like, why would I want some odd power to divide an plus 1? Some odd power of a prime set. Right, okay. So, like, I would want some odd power of this to divide this, because then that would imply at least p divides am plus n. Very interesting. So, oh my God, I understand the writing must be so terrible now. Am plus n. Why? Otherwise, the square has, say, odd VP. Uh, yeah, which it can't because like it's a square. It must have even VP. Okay, no. Like, a better way to raise this for this class is like just see through things. Like it is not that deep. Anyways, yeah, okay. So what would it mean? Like the key point I want to understand is what would it mean if P is dividing, like if we can find some odd power dividing an plus 1, then what would it an plus n, then what would it mean for an plus n? Like this is a very shift perspective, no? Perspectives, no? So yeah, like if an congruent to minus m mod p, but an not congruent to minus m mod p square, we would have that p divides an plus m, but p square does not divide an plus m. Okay, but uh, let us fix n. This is fixed. Like, can we find some n such that this is satisfied? Can we find some m such that both of these conditions are satisfied? Anyone? Like, in fact, in chat too. Like, link this part to the previous discussion which we had on a certain theorem. So yeah.
Can you repeat the question again?
Okay. Suppose we fix them. Suppose we fix them. Then an is fixed, right?
Yes. Yeah.
Now we want to choose some an. We want to choose some m, some number m, uh, such that this is congruent to minus m mod p, and an is congruent, is not congruent to m mod p minus m mod p. Can we choose some m? Like, how can we choose some m? Like, I'm telling you this is possible, but why is this possible?
Mod
This
p
was the
square.
question.
Okay.
Mod p square. Yeah, my bad. Yeah, you are right. Now, my question is, why is this possible? But let me go and turn on the fan though. It's getting very hot here. Like the weather is like changing. Okay. So the point is, to sum up our previous discussion, we would have that uh, if C and D are actually, wait, no. In fact, you can just look at mod p square though. Like take a m congruent to take m as minus an plus p. Yep, this would work. So minus m is congruent to an minus p mod p square. Note that this is obviously divisible by like p. I leave that as a, like. Can you see why this, like, an plus minus an plus p is divisible by p? Like p divides this thing.
Yes. Yeah.
Yeah, because like an and an cancel out and p divides this thing. GG. But now, can you also notice that p square does not divide an minus an plus p, right? Because like this an cancel out, p square must divide p, which means that p must divide 1. Like we can just take these factors out, which is like obviously not true. And also what I mean by this is like, don't take m explicitly as p minus an. Take this as some number such that like uh such that this is congruent to p square mod, like mod p square, this is congruent to that thing. Like if I were to frame it without using modular terms, I would write it as like, take m as minus an plus p plus kp square, such that p square, such that k is like a very large number. K is very large. The kp square is greater than an uh, plus p, implies kp square plus p minus an is a very large number. So yeah, this is valid. And you can just notice again that p square divides this thing, but p square does not divide this thing, and blah blah blah. Stuff happens. Trust. So now, okay. Now, once you choose that kind of m, what would you get? Am plus n times an plus n. Choose, say, not m, m as kp square plus p minus an. Then this is this kp square plus p times am plus n, p times kp plus 1 times am plus n. Okay. So now this is obviously not divisible by p. This is this is divisible by p, but not by but this is not an even power of p. And since this entire number is a square, an even power of p must divide this. An odd power of p must divide this, so that both of them combined together would have like an even power divided this. Why? Because like odd plus odd is equal to even. And what is the smallest odd number? What's the smallest odd number? Okay, I'll just answer that for you. The smallest odd number is this one. Yeah, I'm trivially. So we have that p must divide am plus n. What about minus one? That is so sad, na? Like as if we went. Oh my God. Wow. Uh, anyways, uh, we must have is that p divides am plus n. But what is m? M is just some random number thrown to us by space or God himself, such that m is congruent to minus an plus p mod p. So for all numbers satisfying mod p square. So for all numbers satisfying this, we must have that. Uh, yeah, for all numbers satisfying this, we must have this. Like, this is like you can look over. Like, is this clear to everyone? Like, I think I might have rushed over a few details or stuff, but like, yeah, actually, you don't even need this. Like, if you get it, like that's well and fine. If you don't get it, that's perfectly fine because the next part we are gonna do is like gonna make things a lot more clear. So now, after seeing this, we are motivated by the fact that we can form some claim, and claim forming is like claim conjecturing is a very big part of math olympiads, and in fact, bigger things too. See, like take Fermat's last theorem for example. Fermat's last theorem was not really proved with the intent of proving Fermat's last theorem, no. It was some like random electric curve conjecture. Now, if someone had not, if some random human being would never have conjectured such a thing, like we would not have a proof for Fermat's last theorem, probably. No, like I forgot the name of the conjecture. Can someone look it up for me? Like, what was it called? Like the conjecture which, after being proven, enabled uh, what do you call that? Fermat's last theorem to be proven. Like, point is there was some conjecture. If some human being never thought of that conjecture, and hence, like, we'd probably never be able to solve that conjecture because, like, yeah, math is hard. So we would never have the proof of. Uh, okay, wait, we have a proof for like I'll read it up like shortly enough. But if nobody had ever thought of that conjecture, basically we would not have Fermat's last theorem proved. So yeah, that's like very insane. Conjecture forming is like the if you can in a hard problem, if you can mostly form like important conjectures, like you are basically halfway done through the problem because then the next part is like standard. You'll get through them. You'll after enough practice, you'll be like very good at math, at least in the non-intuitive part. And when you gather that intuition, you are basically like 50 plus 50 is equal to 100% way ready to solve problems, hard problems, in fact, because the easier problems don't really require too much intuition to like think of. So in this problem, as someone someone in the chat said, my solution was like assume a prime p dividing an plus minus a n plus 1 minus an. Then we just need to find some c, so for which one of an plus 1 and an plus c, a underscore n plus 1 plus what both have odd power of prime p. Then we can do a beautiful contradiction. We can do some bounding and prove. an is equal to n. So essentially, the last bounding part is indeed like induction in some sense. But like the actual solution is like, I think you might have missed the detail because the actual solution set is like, if you guess the solution set, like if you try to check if an plus some constant k works, like this works because m plus n plus k times n plus m plus k is a square. Like this entire thing is just m plus n plus k square. But yeah, you are basically right. The point is claim if p divides a m minus a n implies p divides m minus n. Like this is so important. I like color. Okay, no, this is not coloring it. Yep. Insert a few boxes so that like it looks better. Uh, yeah, this is the beautiful claim which we had. Anyways, so claim if p divides m minus n implies p divides m minus n. We can motivate that claim from here only. Like where we have chosen am is equal to m plus k. Like give it some thought. You'll find that this is actually very beautiful. How we motivated such a random claim from such a non-random thing. Because we would usually want odd VPs to happen. As someone said in chat, both have odd power of prime P. Yep, exactly. So that's the main motivation about this problem. And after this, it's just filling out details. Like this claim in itself is not very hard, but it's still like something. So like I would want you guys to like prove this. And in fact, like the person who sent the message in chat, like can you like uh try to write up a entire proof or something about this, or like just write up a nice sketch. I mean that is a sketch, but like yeah, you can do some stuff like for the that thing. So yeah, okay, nice. Okay, I'll give you all some time, like say 2 minutes to think about the problem, and like till then I'll be gone. So like write stuff on chat. I'll like uh, come back and read because like you have to stay hydrated these summers, no? And yeah, that's basically. Okay, I realized the summer is actually like transformed from like summer to like rainy monsoon, but like, whatever. Like just stay hydrated. Okay, I'm here. Like I read through the chat, the the proof sent here, like by some person, is like, yeah, that's basically the correct approach. So yeah, first of all, like you just try to prove this thing. Wait one second. Claim if we have some number s such that VP of s plus an and VP of s plus am is congruent to 1 mod 2, so basically odd, then we are done. Okay. So this is what some person wrote in the chat. Yeah, that's basically it. And why would this finish? Because then, since the VPs are odd, uh, then like consider the number s plus an times n plus as after substituting s as m. And since this is a perfect square, and the VP of this is odd, VP of this would be also odd because odd plus odd can only give even, odd plus even cannot give you even numbers, unless of course. So P divides n plus as. That's great. But similarly, you can get P divides m plus as. Since this is true, what would that mean? P divides m plus as minus n plus as, or P divides m minus n. And this would prove our claim, no? Because if P divides am minus an, then P divides m minus n. So it suffices to find some s. Okay. Now what? How do we in fact find the how do we find the s? Like if I were you, I would have motivated this as so. First, we have played with the problem and found that lots of stuff about P could be like satisfied. We can find lots of interesting M. So since we can find lots of interesting M, we can find lots of interesting conditions. So yeah, I would like try to formulate this claim, since I would notice that as the person in the chat said, an plus 1 minus an uh, would not be divisible by any prime, and hence like you would have some stuff which I'll like deal with later. If that number is not divisible by any prime, it must be 1 or minus 1. So yeah, and that would like after that the problem is pretty easy. I like in fact leave this as a Hilbert. At that point, it's not even like number theory; it's algebra, which is like basically shifting perspectives again. So yeah, but now how do you find some s? Like basically, just if uh if VP of am minus an is congruent to is like equal to 1, we'll case bash. If VP of am minus an is equal to 1, choose s is equal to p cube r minus an. Okay, where uh, r GCD of r and p is equal to 1. What would that mean? We would have that am as plus, no, sorry, we would have that s plus an is congruent to p cube r is equal to p cube r, in fact. Uh, but see, this has like odd VP, right? So basically, what we are done with the problem. No, in the case VP of am minus an is equal to 1. Is that fine with you all? Like, can anyone like say if this is fine, or should I like go over stuff like, really quick? Like if any problem, anything in regarding the motivation for this problem, or basically anything, please ask. Like if you ask, you're gonna learn a lot of things, and I'm gonna learn more than you, in fact, because like I'm coping right now. But yeah, so asking questions is like a very big art in itself. So you should ask some questions if you have any, obviously. Like, if so, I'll like take that as a no, I guess. Yeah. Okay. And similarly, uh, one sec. At s plus am, notice that this is like congruent to p cube r minus an plus m. But we have already have that p divides am minus n. So this thing just vanishes because this is divisible by p, and like the VP of this entire thing is just odd. Oh no, this does not really vanish, no. P cube R minus AN plus AM. Highest power dividing highest power of P dividing this is PQ. Highest power of P dividing this is P. By our assumption, VP of AM minus AN is equal to 1. So uh yeah, like just consider an example for this case. It's not really hard to prove, like, but I like to demonstrate with an example. Suppose 5 cube minus 5. What's the highest power of 5 dividing this? Anyone? Like, please answer this.
1.
Exactly, yep. Oh, wait, Lamin Yamal. That's crazy. Insane support. Anyways, yeah, this is 1. Why? Because we can factor it as 5 square minus 1 times 5. But now, since this is 1, like, the entire VP of this must be 1, since this is, like, not divisible by 5, clearly. So, in fact, uh, uh, yeah. So, we are done in that case, no? Because we have found S such that uh, S is equal to P cube R VP of AN plus S is equal to VP is congruent to VP of AM plus S is congruent to 1 modulo 2. Now, since we have this now, we have found such a S, and we we are done if we have found such a S because of the proof here. Hence, like we are done if we have found such a S, no? So then we'll be done with this claim, and then we'll move on. Now, what if the case is VP of AN plus S, VP of AN minus AM is odd? This is the second case, by the way. What if VP of AN minus AM is odd, but uh, what are they trying to say? Yeah, but it's not equal to 1. Okay, so in that case, it's like even easier. This set proof is this set S is equal to PR minus AN. Then where GCD of R and P is equal to 1, then we would have that PR minus AN plus AN is equal to S plus AN, implies like PR is equal to S plus AN. But now, what is the highest power of P dividing PR, where R is odd? What is that? Can anyone answer real quick?
1 again.
1 again. Exactly. Now, since the VP of this is odd, but also consider the number PR minus an plus am is equal to s plus am s plus am, which is equal to pr plus am minus an is equal to s plus am. Now, what did our assumption say? VP of an minus am is odd, but it's not equal to 1. What would that mean? What's the smallest odd number after 1? Like a natural number, obviously. Uh, so yeah, it's 3. Exactly. Yep. Since it's 3, we have that p cube must divide this, right? P cube divides this, right?
Yes.
Exactly. So, but p divides this. So again, we run into a situation where p cube times something plus p times another thing. Now we want to find the VP of this, or like the highest power of prime divide is this. Similarly, 5 cube
That
plus 5.
right. That'll just
Huh?
be one. This will be one,
What?
right? This will be
VP
one,
of?
right? This
Yeah,
thing.
this is just one. Exactly. So in fact, we have found such a S such that the VP of this thing is 1 and the VP of this thing. In fact, we don't even need this. What is this? I'm coping. Uh, is greater than 1. So this is like at least 2. So this is a 5 square plus 5 type of case. At like this is similarly 1. So yeah. Uh, so now we have shown that the VP of S plus AM and S plus AN both are equal to 1, and 1 is clearly an odd number. So we have found such a S such that VP of AN plus 1 is AN plus S is congruent to VP of AM plus S is congruent to 1 modulo 2. In fact, this is equal to 1. But from this claim, we have that we are done. But what are we done with? We are basically done with this claim. So see, we are claim jumping in some sense. So yeah, okay. Now we come to the interesting part. Like this is still a very important detail which people could miss. In fact, I missed it the first time I tried the problem too. That like m minus n, p divides am minus an implies p divides m minus n. What if you take m is equal to n plus m, n plus 1? Then p divides am plus 1 minus an plus 1 minus an implies p divides n plus 1 minus n implies p divides 1,
Not
which
possible.
can't happen. Not possible. Exactly. So what does this tell you about the number an plus 1 minus an? At the base level, it tells you that no prime divides this number. There's not a single prime in this universe that divides this number. And how many numbers do we have that no primes divide? Like how many numbers are there in integers such that none of the primes divide the number? Like divide the number. Say there's some number x. No prime divides this number. Then what must be x? Like there are two possible values of x. 0 is not one of them. So what is x? Plus minus 1. Exactly. Yep. So now an plus 1 minus an is equal to plus minus 1. Isn't this very beautiful in some sense? Like suppose you have some number initially a1 is equal to c. Then a2 would be c plus 1 or c minus 1. And a3 would be say c plus 2 or c or like c minus 2. Interesting. So now you have like very nice structure about the problem entirely. And in fact, uh, you can go on to proving that the only solution which works is am is equal to uh, m plus c. Let this be c plus 1. So M plus C. Okay. This is our only solution. You can check this like clearly. But then also what we would have is that but what we would need to do to prove this is that M plus C, that the case where we jump from A1 say is equal to C plus 1 to A2 is equal to C plus 1 minus 1 can't happen. And instead, what should happen is C plus 1 plus 1. You would have to prove this. This is like fairly easy compared to the number theoretic discussion we just had. So I'll like leave this as a homework to you guys. So to you guys. So like what you basically have to prove is you are given a sequence, blah blah blah, and you know that AI plus 1 minus AI is equal to plus minus 1. The entire sequence is natural, obviously. And A1 is equal to C plus 1 for some whole number C. AM plus N times AN plus M is an uh, is a perfect square. So this is your homework, guys. Implies what this then prove that AM is equal to C plus M. So this is a homework question, guys. Like you can take the screenshot of this, but I'll like send it over like OMC's, what do you call those? OMC's sources and recordings, whatever you call those. So yeah, this is your homework, guys. Because then after proving this, we are basically done with the problem. And hints for this problem are like one of the hints is this induction. Like just induct on this problem. You all had a class on induction yesterday, no? So like see, it complements so well. Like yesterday you learned induction and now you're using it like obscurely in a random number theory problem. Well, not really random, but yeah, a number theory problem. So like lots of things are very interconnected in mathematics in general. And like like people start calling maths beautiful. Like when I was like very young, I did not understand why math was really called beautiful. But then like the thing which worked for me to realize this thing was noticing how many different interconnected paths are there, how many things are interconnected, and how obscurely they are interconnected. So yeah, again you induct here. Even though this is a very, very small example in the big sea of things, you'll when you go on like the next month, the next few months, you'll like realize a lot of interesting stuff, etc. So yeah, this that. So yeah, I think we are in a position to end the meeting now, end the class now. So let me just stop the recording.